When a Tesla dies, most people picture a junkyard and a slow fade into rust. That mental image is outdated. A modern battery does not just go away. It goes somewhere. And where it goes next decides whether the battery story ends as a waste problem or becomes a materials story. This is a battery recycling gigafactory, not a garage, not a scrapyard. A real industrial system built around one brutal reality. A large lithium battery is not dead in the way people think dead means. Even when a car cannot drive, energy can still be trapped inside. Cells can be damaged, conductors can be exposed. A short can exist for months and then suddenly become a fire in seconds. So the first part of this process is not shredding. The first part is control. Everything you see here has one job: keep a chaotic object from becoming an uncontrolled event. You see distance, barriers, sealed containers, ventilation, secondary containment. You hear constant airflow. You feel vibration through the floor. It is not dramatic in the way the internet wants. It is disciplined in the way industry demands. Battery packs arrive and they get treated like high-risk freight because that is what they are. The workflow starts with staging and inspection. Nothing glamorous. Verifying condition, checking for obvious physical damage, looking for leakage, swelling, crushed areas, burn marks, or missing colors that can expose conductors. This is where satisfying destruction gets earned. If a pack looks wrong, it does not get rushed into the line. It gets isolated. Because one compromised pack can shut down an entire facility, it can contaminate a work area. It can trigger an emergency response. The line does not exist to create viral footage. The line exists to run tomorrow. The next reality check is that batteries are not uniform. Even within the same vehicle brand, you can see differences in design, module geometry, fasteners, and protective structures. People online talk like every battery is the same black brick. That is fantasy. In real plants, variability is a daily problem. The entire front end of the facility is designed to handle variability without turning variability into chaos. There is another unpopular truth. Transportation and handling are part of the risk. The pack can be safe in one state and dangerous after a bump, a drop, or a pinch point. That is why everything here is clean but used. Scuffed floors, worn rails, stainless surfaces with fingerprints. It is not a showroom. It is evidence of real work done repeatedly with systems designed to protect people and equipment. Before any pack can be physically reduced, the operation has to ensure it is safe enough to process. That can involve isolating terminals, using approved handling fixtures, and routing packs through controlled steps meant to reduce the chance of an internal event. I'm not going to give you a replicable how-to, because that would be irresponsible and unsafe. The point you need to understand is simpler. This is a safety engineering problem first, and a recycling problem second. If you skip that order, you do not get recycling, you get downtime. Now we move toward the mechanical heart of the plant. This is where the sensory experience changes. The air is louder, fans push and pull, motors whine at a steady pitch. You hear metal on metal in the distance. A facility like this never goes silent because silence is not your friend. Silence can mean a shutdown, and a shutdown can mean a problem. You start seeing the machines that make recycling possible. Conveyors, hoppers, sealed chutes, magnetic separators, screening decks, air classification columns. None of these are exciting alone. Together, they are a choreography designed to turn mixed debris into usable streams. And now we get to the moment people came for, shredding. A shredder does not just break things. It creates the conditions for separation. A battery gases when damaged. That is why modern lines often shred under suppression. Sometimes that means processing under a liquid surface. Sometimes that means a sealed environment with aggressive containment and extraction. The visual is dramatic. The bite of cutters, the tremor through guard rails, the occasional flash that dies instantly. The reason it dies instantly is the engineering around it. The drama you see is not the point. The point is preventing the drama from becoming a fire. When the feed begins, everything vibrates. The guards hum. The line breathes. Shredded material exits as a messy stream, torn aluminum, copper fragments, bits of steel, plastics, and the thing we are actually hunting, fine powder. That powder is the core of the value story and the core of the risk story. Fine powder wants to float, it wants to cling, it wants to migrate. So the facility treats dust like an enemy and like a product at the same time. That is why you see sealed transitions and aggressive extraction at transfer points. That is why workers wipe seams, not because they are neat, but because a thin line of powder on a gasket can become a leak. A leak becomes contamination. Contamination becomes rework. Rework becomes cost. And a dust event can become a shutdown. That is the chain nobody wants, but everyone here is thinking about. After shredding comes separation. This is the part that looks boring until you realize what is happening. You are taking a pile of chaos and you are extracting order from it, using physics. First, you remove ferrous metals. Steel responds to magnets cleanly, so magnetic separation can peel it away quickly. That steel stream can become its own recyclable product. Then you start splitting by size. Screens and sieves separate larger pieces from fines. Larger pieces might include aluminum and copper fragments, plastics, and casing material. Fines contain the active material concentrate, but they also contain a lot of unwanted dust and small debris. The line is always balancing yield against cleanliness. Then you separate non-ferrous metals and plastics. There are multiple industrial methods for this, but the principle is consistent. You keep narrowing the stream until you have a fraction rich in what you want. Air classification can lift lighter fractions and let heavier particles drop. Density-based separation can help split materials with different mass characteristics. The exact machine choices can vary, but the goal does not. Isolate black mass while keeping metal pieces and plastic pieces in their own controlled streams. At every stage, you are fighting cross-contamination. A little aluminum in a copper stream matters. A little copper in a black mass stream matters even more. If you want refined output, you cannot be casual here. That is why quality control shows up constantly, even when the camera is not looking for it. And this is where a simple object becomes the anchor of the entire story. A scratched stainless sample tray with 3 circular wells and a black rubber grip strip. It is not glamorous, it is not big, but it is real. In those wells you can place tiny amounts of material that represent the health of the entire run. A pinch of black mass, a sample of lighter fraction, a droplet from a process stream. That tray is what separates serious plants from content farms. Because real facilities do not guess, they sample. So what is black mass? Black mass is the concentrated fine fraction containing battery-active materials, often mixed with graphite and other fines. It can contain lithium, nickel, cobalt, manganese, and other components depending on what was processed. It is not pure. It is not ready to build a new battery. It is an intermediate. It is modern ore. And it is messy. It behaves like dust. It stains. It clumps. It can be reactive depending on what it contains and how it was produced. That is why the facility treats it like a product that must be contained, not like dirt you can sweep anywhere. Black mass handling is where you see the discipline get sharper. Sealed containers, tight clamps, enclosed transfers, dust extraction arms positioned like sentries. Everything is designed to stop the powder from becoming airborne. Because airborne powder is not just a cleanliness issue. It is a safety issue and a product loss issue at the same time. This is also where the story forks. Some operations focus on producing black mass as a sellable intermediate. Others refine it further on site. This gigafactory is built to go further into chemistry. That is the step most people do not understand, and it is where the electric car waste narrative either collapses or gets justified. If you stop at shredding, you have created waste streams and a powder stream. If you refine the powder stream into consistent products, you have created a loop. But let's be honest, that loop is not automatic. It is earned. It is earned through chemistry, filtration, cleaning, and constant verification. It is earned by preventing contamination and by keeping the line stable. Now we step into hydrometallurgy. That is the realm of wet chemistry, where liquids are used to selectively move metals into solution and then separate them into distinct products. This is where the process stops looking like demolition and starts looking like manufacturing. You notice the environment change. Less dust haze, more humidity haze, stainless piping everywhere, sealed vessels, pump hums, controlled agitation. A place designed to handle liquids without turning them into spills and without exposing workers to hazards. At a high level, the first chemical operation is leaching, converting the valuable metals in black mass into a liquid phase where they can be separated. I am keeping this high level on purpose. The point is not the exact chemical recipe. The point is what the facility is doing conceptually. It is taking a mixed solid and turning parts of it into a controllable liquid stream. Inside closed vessels, slurry swirls. The motion is contained but constant. Hoses pulse. Valves cycle. Condensation beads tremble on a pipe elbow. Every vibration is telling you the system is alive. Every joint and seal is telling you the system is trying to prevent leaks. This is where the stakes shift. On the mechanical side, your risks are heat, sparks, and dust. On the chemical side, your risks are corrosion, incompatible mixing, off-gassing, and contamination. Different risks, same discipline. Then comes solid-liquid separation. Filtration is a gate you cannot fake. Filter presses clamp and compress. Plates hold pressure. Liquids move through membranes. Solids consolidate into cakes. The sound is heavy. Hydraulic thumps, metal clacks, the low groan of a system holding force. This is also where quality control becomes a make or break moment. If the filtration is not right, you send fines downstream. Downstream fines can foul equipment and contaminate products. If the filtration is too aggressive or unstable, you can lose yield. So the facility samples, checks consistency, and watches for signs that a batch is drifting. That scratched sample tray returns again and again. A damp crumb from a filter cake in one well. A small portion of dried granules in another. A droplet from a process stream in the third. The tray is not decoration. It is the physical proof that this plant lives on verification. Once solids are separated, the liquid stream can go through a sequence of purification steps designed to isolate different metals and remove impurities. This is where the process becomes less intuitive for viewers. It is not one magic step. It is a chain of adjustments, reactions, separations, and polishing steps. The reason the chain exists is because you are trying to produce consistent, usable outputs, not a vague slurry that nobody can rely on. If you want the truth, this is where many recycling stories fall apart. Not because it is impossible, but because it is hard. It requires capital, engineering, and discipline. If you cheap out here, you produce inconsistent material that cannot be used at the level people claim. That is why recycling is not one thing. There is recycling that makes content and recycling that makes products. As the chain progresses, you start seeing solids that look nothing like the black mass that started the story. Fine crystals, pale granules, clean-looking powders that pour and settle, materials that can be dried, packaged, and moved with less drama than the beginning. That visual contrast is the real payoff, a dark, messy concentrate turning into something controlled and consistent. Drying systems remove residual moisture and stabilize the product. Warm airflow hums. Exhaust vents breathe, trays slide on rails. Granules cascade in thin layers and settle with a soft hiss. The process looks calm now, but calm does not mean casual. Fine powders still create dust risk. So extraction remains, housekeeping remains, seals and clamps remain. Then comes packaging. This is where the facility makes a promise to the outside world. What leaves here is contained and verified. Containers get seated, clamp rings tight, seals get checked, surfaces get brushed clean, not for aesthetics, for shipping integrity. You see the small rituals: tap the clamp ring, tug the strap, confirm the lid seam. These rituals exist because a compromised container is not just a customer complaint. It can be a safety incident, it can be a spill, it can become a regulatory problem, and it can damage trust. In industrial materials, trust is a product. A serious line has a final verdict moment, not a speech, not paperwork on camera. A simple signal, a status ring light and a latch. A steady green glow that means the batch is cleared to move forward. It is intentionally boring because boring is what you want at the end of a process that started with shredding batteries. Now logistics takes over. Pallets get wrapped. Stretch film tightens and creases. Forklifts glide, align, and stop with precision. You can tell the operators are trained because nothing is rushed. The forklift does not slam. The pallet does not wobble. The load stays stable. Shipping bays have their own logic. Air curtains can help keep dust and outside air from mixing with interior air. Doors lift. Motors whine. The outside world is inches away, but the facility keeps its internal discipline. Dust stays inside. Containers stay sealed. The product leaves clean. Now we loop back to the bigger question everyone argues about. What happens next? The most honest answer is that recycling only closes the loop if the outputs are consistent enough to be used again. That is not a slogan. That is a manufacturing requirement. If you cannot produce reliable materials, you are not closing a loop. You are delaying disposal. When this process is done right, the output can feed into manufacturing again. The refined materials can become part of electrode production. Coating lines can apply active material mixtures onto metal foil. The foil can be dried, calendared, slit, and wound. Layers can be stacked. Pouches can be sealed. Cells can be formed and tested. Packs can be assembled. The material can return to the road. That does not mean every atom comes back. It does not mean it is effortless. It means the most valuable parts of a battery can be recovered and put back into the supply chain in a controlled, verifiable way. That is a real improvement over a landfill narrative, and it is also not a fairy tale. It is industrial work. But here is the part I am not going to romanticize. This is still a high-stakes operation. It is not just about environmental messaging. It is about economics, safety, and uptime. A single event can shut the line down. A single contamination pathway can force rework. A single uncontrolled dust release can trigger safety responses. Every step has a cost. Every check has a reason. So if you came here for satisfying destruction, you got it. But the destruction is not the story. The story is what happens after the destruction. The story is that a facility like this can take the most dangerous part of modern transportation and turn it into feedstock with discipline. And that is why that scratched sample tray matters so much. It is a simple object that forces the truth into the open. 3 wells, 3 snapshots, 3 reminders. Black mass is a beginning, not an endpoint. It is a concentrate that must be proven, refined, and packaged with the same seriousness as any other industrial product. Now, I want you to watch the loop in your mind, because the ending is the point. A sealed pack arrives as a risk. It gets controlled. It gets reduced under suppression. Mixed debris becomes separated streams. Fine powder becomes black mass. Black mass becomes controlled chemistry. Chemistry becomes purified streams. Purified streams become solids. Solids become packaged product. Packaged product becomes a supply chain input. A supply chain input becomes a new battery. That is the ultimate loop. The old car becomes part of the new car. And the final irony is this. The part that looks like dirt is the part that drives the value. The black powder that stains everything is the bridge between yesterday's battery and tomorrow's battery. If you lose control of it, you lose the loop. If you refine it with discipline, you create a second life for the materials that used to be locked inside a pack. So the next time someone tells you electric car batteries just pile up and rot, you can answer with something real. They are not wrong that batteries create a waste challenge. They are wrong that there is no industrial answer. The answer is not a slogan. The answer is a facility built to control risk, isolate value, and prove output. And if you want the full story, the story most clips skip. It is the quiet parts. The sealed transfers, the extraction, the filtration, the sampling, the wipe of a gasket seam, the tug on a strap, the green ring that means the batch is cleared. Because shredding is easy to watch. Turning chaos into usable product is the hard part. And that is what this place is built to do.